Imagine trying to find a handful of specific records buried inside a multi-gigabyte, globally distributed database without downloading the entire dataset. That is the core data syncing challenge for lightweight network clients. But there is a secondary, much harder constraint. You have to extract your data without letting the network know exactly which pieces of information you actually own. In the early days of Bitcoin, developers proposed a mathematically elegant solution to this problem, BIP37. It relied on a probabilistic data structure known as a Bloom filter. The theory was brilliant, but when deployed into the live, adversarial environment of the Bitcoin network, the system fractured. The vulnerabilities were so severe that Bitcoin Core eventually had to disable Bloom filter support by default, actively rejecting client connections that relied on them. The deprecation of BIP37 serves as a masterclass in systems architecture. It exposes the critical difference between localized mathematical obfuscation and functional network privacy. Deploying a theoretically secure data structure is ultimately useless if you fail to account for the underlying topology and the relational nature of the dataset itself. To understand why the protocol failed, we have to look at how a Bloom filter actually works. At its core, it is a highly space-efficient, probabilistic data structure designed specifically to test set membership. It operates using two foundational components: a variable size array of n binary digits, which starts initialized entirely as zeros, and a variable number of deterministic hash functions, which we'll call m. To visualize this, look at this 16-cell grid. It represents our simple array of zeros, and the three conceptual pathways pointing toward it act as our hash functions. When you want to write a pattern into the filter, you pass your input through each of the hash functions. Deterministic hashes always output an index between 1 and n. We take pattern A and hash it 3 times. The filter locates these 3 indices and flips the corresponding bits from 0 to 1, permanently recording the pattern. The complexity arises when you add multiple items. As the filter absorbs data, a hash might output an index for an already flipped bit. Running pattern B, one hash lands on an active bit. It remains 1, while other hashes flip new cells, increasingly saturating the array. This saturation dictates how we query the filter. If we search for a new pattern, hash it, and even a single resulting index points to a 0 in the array, we have absolute mathematical certainty. That pattern is definitively absent from the set. However, if we hash a search pattern and all the resulting indices point to 1s, the answer is only a maybe yes, because those bits could have been flipped by the overlapping hashes of completely different patterns. A positive match is strictly probabilistic. System architects tune this behavior based on their exact needs. By expanding the array size, n, or altering the number of hash functions, m, they can dial in the precise ratio of accuracy to privacy. The mechanism guarantees 0 false negatives, while intentionally allowing a mathematically controllable volume of false positives. It's a highly efficient way to compress data queries. Lightweight Bitcoin clients applied this probabilistic math directly to distributed networks. To synchronize with the network, a client app on a phone or laptop initializes a completely empty Bloom filter. It then scans its own wallet, extracting the public key hashes, script hashes, and transaction IDs from its unspent transaction outputs. The client processes these unique identifiers through the hash functions, recording them all into the filter. Instead of asking the network for specific addresses, the client compresses its T's into this tiny bit array and transmits that compact block to a fully synchronized peer node. A filter load message transmits this block, establishing filtering rules for the connection. The full node receives the array, acting as a gateway. It takes the heavy, continuous stream of incoming transaction blocks and runs them directly against the client's filter. This places an immense computational burden on the full node. For every single transaction, the node has to check the transaction ID, the script data components, all the inputs, and the witness data to see if any of it triggers a match. When the filter flags a positive match, the full node packages the corresponding block headers and the specific transaction data, routing it back to the lightweight client. The client receives the data, discards the false positives, and updates its wallet balance. If it discovers new transactions referencing its outputs, it dynamically modifies the Bloom filter to include them and sends the updated filter back to the node, repeating the loop. On paper, BIP37 offered an elegant theoretical privacy model. The client could retrieve its genuine financial data securely hidden within a dense fog of mathematically generated false positives. In a purely mathematical vacuum, the full node has absolutely no way to distinguish the client's actual wallet activity from the random static generated by the filter. But a blockchain is not a mathematical vacuum. When subjected to real-world relational data analysis by adversarial nodes, that theoretical privacy model completely collapsed. An adversarial node operator could simply log the entirety of the requested transaction set and hold it for post-processing. Once logged, a fatal structural difference emerges. The false positives generated by the filter are statistically isolated anomalies. Genuine wallet transactions, however, share strict, predictable parent-child relationships from output to input. This scatterplot visualizes the raw data returned by a Bloom filter as an undifferentiated mass of noise. But because Bitcoin transactions are inherently linked, tracking inputs and outputs reveals a structured chronological chain. The unconnected noise drops out, leaving only genuine data points. By applying basic graph analysis to those input and output links, an adversarial node could effortlessly strip away the mathematical noise and fully de-anonymize the client's wallet. Beyond the privacy leak, the protocol harbored a severe physical vulnerability, an asymmetric computational load. Because the full node does the heavy lifting, a malicious client could intentionally craft a highly saturated filter. This forces the serving node to perform exhaustive, computationally expensive checks across the entire history of the blockchain. A low-effort request from a client forced massive server computation on the full node. This asymmetry created a highly effective denial-of-service vector against the network. Confronted with the total failure of its privacy model and severe physical risks to network stability, developers deprecated the protocol. The industry was forced to seek alternative syncing methods. The failure of BIP37 is a critical case study for protocol engineers. It highlights the fatal disconnect between the flawless, abstract perfection of bit array mathematics and the messy, highly relational reality of a blockchain's transaction graph. Look at this contrast. You can design a perfect statistical shield on the left, but it will shatter if it ignores the actual shape of the underlying dataset on the right. Mathematical obfuscation only provides true privacy if the data you are hiding is entirely uncorrelated. If a dataset contains inherent structural relationships, topological analysis will always pierce localized cryptographic masking. The connections between the data points will always betray the data itself. In closed, non-adversarial environments, Bloom filters remain incredibly powerful and efficient tools for rapid set membership queries. But as Bitcoin learned the hard way, mathematical brilliance is not enough. Probabilistic data structures cannot serve as a reliable foundation for adversarial network privacy.